Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
Robert, this is episode 25, season 2, and it's the Halloween edition.
Ooh.
Spooky.
Spooky.
So what are you dressing up for Halloween? Are you dressing up at all,
I
Robert?
am not dressing up. I don't get any trick-or-treaters coming by my apartment or anything like that, so I just don't see much. I don't see much reason for it other when I'm just doing it for me.
Well, that's funny. I could have sworn I seen you in the store the other day buying bags and bags of candy. Who are they for? Should I ask?
If you saw me doing it, they're for me. Yeah.
Well, Robert, what do kids say when they go to doors looking for candy?
Trick or treat.
Trick or treat.
Smell my feet. Wait.
Give me something good to eat.
Yeah, something like that.
Did you ever hear the expression shell out?
No.
That must be a Canadian expression.
Okay.
So, because trick or treat means you either get a treat or a trick, and you don't want the
trick
part of it. So in Canada, I assume this is where it comes from. At least this is what I was told when I was younger. That you say shell out instead, so then you get candy. Shell out your candy to
Got it. Okay.
rather than getting a chance of getting the trick part of it. You see?
Right.
I figured you probably wouldn't have heard that expression.
No.
That must be a British-related Canadian. I have to look that up in Google, everything else, and see where that actually originated.
It's kind of like the old terms of wassailing and all that for Christmas time. You know? Old angsyne, it's like, okay. Anyway.
Anyways. So I have a treat for you, Robert, today.
Okay.
And this is a treat that I want you to open up in front of everybody on the podcast. So be careful, don't wake it.
Okay.
Don't wake it up.
Okay.
And remember, it goes to the bathroom at least twice a day.
Right. And don't feed it after midnight?
Yeah.
All right.
Be very careful now opening that up.
Yeah.
There's a trick to it. I'll let you struggle a little bit, then
is.
you found it. Make sure you get it in the camera now.
Okay. Oh, wait.
There you
Gotta go in reverse direction. Okay. It's not going to jump out at me.
No, it's quite dead.
Oh, look at this. Woohoo!
Your very own Cosmic Pie mug.
I like it.
Robert, we have merch.
You have merch? When did this happen?
It just happened a few days ago.
Is it available generally? Or?
No, we need a sponsor to pay for it.
Okay.
So if anyone out there of higher powers who makes more than we do, if they're listening,
I would hesitate to say that, and that should segue into
our disclaimer. Anything Robert and I say are strictly our own personal opinions, have nothing to do with the University of North Dakota or anyone affiliated with it. Now let's continue that conversation.
Let's consider that.
Some of the rich people who might be watching this, can you please cough up some money to pay for some merch?
Right.
And
That'd
we'll
be
gladly
wonderful.
send it out for those who want it. I don't know if we could do that. But
I don't know if we can do that
go bankrupt.
because that would be, money that would not be tied to any university account. So I imagine they'd have problems with it.
I wonder if we could do anyone who's a guest on our podcast, we send them a mug for being a guest.
Now that might be interesting. We'll have to chat with people about that.
If the university would go for that.
Yeah.
Well, who knows?
Yeah.
Anyways, so welcome to the Cosmic Pie Podcast. We do have a live chat feature that's running, so if you have any questions or comments that you would like to send to us in real time so we can answer them while we're doing the podcast, feel free to use that feature.
I got to admit, I'll comment on that too. It's not that we don't like you asking questions in the comments on the videos later. It'd be real nice, though, if we could start getting some back and forth. But at the same time, we're going to keep things on the science level. So, yeah.
Yeah, and it's hard also to answer questions and people make comments later on because sometimes I miss them.
Right.
Like someone might comment on a past podcast, a couple months ago, and sometimes it takes me a while to even notice the comments.
It's going to get swamped in everything else.
Yeah.
I hate to say it, but
we have done well over 60 podcasts now.
Wow. I know there are people out there who are on the thousands of podcasts, but to think it's up to 60 for us.
Yeah, we had to think 42 the first year, and then we're like, 25th one now?
Right.
So we're at 67 This is the 67th podcast.
Okay.
And we still took the summer off this past summer.
And we took the summer off.
And we do take time off for holidays, too, because we have to do our thing. And when things get really busy, like exam time, sometimes we took
We'll take off.
time off, or for traveling.
Yep.
You know, you deserve a merch. You know why? Because you've actually been here on every single podcast from day one.
Yeah, well.
Right? So you deserve that.
Thank you. Thank you.
I mean, I haven't because I've been traveling or doing other things, had doctor's appointments. I think I missed the podcast here and there. And thankfully, we had Dean to fill in for me. So we should give him have to get a mug for him.
Get a mug for him for
Once
sure.
somebody throws us some money our way, I guess we can afford that.
Well, I mean, I could chip in for that.
But we are broadcasting live here from the campus of the University of North Dakota, here in Grand Forks, where the winter is slowly creeping along.
I was about to say, fall is finally starting to rear its head. And
It is.
The temperatures are dropping a bit.
Which is good because it makes it a good scene for Halloween on Thursday evening.
Right.
Which is only like 48 hours away from now. People will be going door to door.
Ding dong.
And we do have a Halloween theme as our first news item. And this is what we call the zombie star.
Oh, the zombie star. Okay, what is a zombie star?
Well, if you want to go to the first slide, Robert.
Yeah.
So this has a long, sort of rich history behind it. It makes an interesting story. So way back in August of 1181, Robert, that was when you were in high school, wasn't? No, just kidding.
Something like that. Yeah.
So back in 1181, it has been reported by both the Chinese and the Japanese in their literature and their different works that they published, that there was a new star that appeared in the constellation Cassiopeia.
Okay.
And the star was visible for 185 days.
Wow.
Yeah.
That is impressive.
That is
supernova
impressive.
don't last that long.
Well, this one, it was nearby. It was in the Milky Way.
Okay.
This distance estimated today of about 7,500 light years. So that's relatively nearby.
That's
That's
nearby.
our backyard. In fact, I'd love to see a supernova in my lifetime that close.
That
go
close,
off.
right?
You know, it's been 400 years since the last supernova went off in the Milky Way galaxy in the time of Kepler.
Right.
So we're long overdue. You know, most of them are probably, some have gone off in the Milky Way, but are usually on the other side from us.
Which means they're obscured.
Yes, which you can't see them because that light would have to travel through interstellar gas and dust, and the dust loves to scatter and absorb light.
Yep.
And that makes things look extremely faint. And unless you're looking in the right spot, and it may make it so extinguish the light so much so that we don't even see any of the light reach here on Earth. So we've been unfortunate, just not lucky, but there have been supernovae gone off in other galaxies, just not in our own Milky Way.
And then at least one in a nearby satellite galaxy, but that's still not our galaxy.
Yeah, that was back in 1987. So supernova 1987. In fact, we had Ian Sheldon on a previous podcast, the discoverer of that supernova.
Yep.
So he talked all about
That
the
was a good
details of that.
podcast. That was a good one.
Yeah, for sure. So this is supernova that went off, back in 1181. So almost 900 years roughly. 900 years ago, roughly. And it was reported, but when people looked roughly in the area of the sky where it was supposed to be, and of course, back in 1181, there's no way to accurately measure astrometry-wise exactly the coordinates of where this object would be. The telescope didn't come along until the very end of the 1500s.
Right.
So this is like 400 years before the invention of the telescope. And so people made a rough outline of where it was relative to the other stars in the constellation that you can see with the unaided eye.
Right.
And people couldn't see the leftover debris from the supernova, what we call the supernova remnant.
Okay.
So we know, like the Crab Nebula is a very famous supernova remnant.
Yep. The Veil Nebula is another one.
Veil Nebula, and there are many other ones. And so that's the leftover debris. Think of a star blowing up, and where does all that material go after the explosion? It gets hurled outwards in all different directions.
Right.
And it creates this nebula-like feature. And we look for that and usually you'd see, okay, the center of it is probably the most likely place where the progenitor of the supernova existed, unless it's somehow was given a kick, which some of them do.
Right.
So it travels off to the side a little bit.
Momentum is conserved one way or another.
And the other thing is, it depends on the alignment, right? You have to worry about that. But so there was a search once in a while for the remnant of this supernova, and it was actually finally discovered not way back, but only recently in 2013.
Oh,
Which is quite interesting. And
That's
the person who
interesting.
discovered, actually an amateur astronomer, Dana Patchik, and she used the WISE infrared data set to actually pick out the supernova remnant, which is quite interesting. And we'll see some slides in a minute here about this, because I'm going to lead into this paper that you see in front of you and what this is all about here in a minute. Like I said, it's a long story, but but an interesting story.
Yeah.
So the infrared is more able to see things through the interstellar medium,
through the dust and
gas. And so it was a little bit easier to pick out the remnant at infrared wavelengths than it would be at optical wavelengths, for example. And once you know where it is, and of course then you can train large telescopes in this exact area,
pick it up easily.
4 and 8 meter class.
How did we miss this?
Yeah, exactly. But you got to know where to look, and the field of view is usually not that large, so it's not like you can take an 8 meter class telescope and scan the whole sky every night. In fact, we're going to do that with the new Vera Rubin telescope.
Oh, okay.
And that's ready. By the way, today it's been announced publicly, and on the project, I work on one of the working groups for it. So I had an inside knowledge of what had happened several days ago, is they used sort of a preliminary camera on the telescope to obtain first light.
Oh, okay.
And that's being released now. And that was they're going to have a much better camera to put on the Vera Rubin telescope, but it's a little over 8 meters in diameter. And it is designed to be a very fast telescope to be able to scan the whole southern sky every 3 nights.
Okay. What does it mean that you have a fast telescope?
Yeah, so we're talking about what's called the focal length, the F ratio of the telescope itself. And so there are different ways you can design telescope. This is a reflecting type telescope, but it actually has a tertiary mirror that's built into the main primary mirror.
Oh, wow. Okay.
So there's the primary mirror, the light gets reflected off that, hits a secondary mirror back to a tertiary mirror. So it's designed quite uniquely. And if you actually, maybe we'll get a chance once the images are released and we get into it a little bit more.
We'll start
do
looking at what it's
podcasts
doing.
of just the telescope and what it's all about. So the design is to survey the southern sky completely every 3 nights and just continue observing it, building up the exposure times by stacking the images.
Right.
And that'll allow us to see, a lot of things that are very hard to capture because you need a wide field of view to see them. Think of asteroids, for example. If you're able to observe the whole sky every 3 nights, you're going to find a lot more of them than you can nowadays.
Because there'll be this moving dot across a field of stationary dots.
Things are moving relative to the stars, and so that's capture your attention. In fact, it's an 8 meter class telescope, which means we're going to be able to see tiny, faint things. But the thing is, it has relatively short exposure times, but over time we're stacking them together. So at least for stationary objects, we can build up a very long exposure after several years.
Right.
So there's trade-offs, of course, with that, right? If you took long exposures at any given pointing on the sky, you're not going to be able to cover the whole sky in 3 nights. It's going to take a lot longer.
It's going to take a lot longer.
So there are trade-offs, right, of all this kind of stuff.
Yep.
Anyway, so the interesting thing about this is that, and this is the paper that's getting into here, is that people have followed up then this object to look at it in more detail. So in particular, there was an image taken a few years ago by Robert Fenson at Dartmouth College. And this is a filtered image taken in the light of sulfur. So what you're seeing is light that's basically sulfur emission.
Yeah.
The image is dominated by sulfur.
Why sulfur?
Yeah, so that's actually created in a here's the interesting part, and it's in the title. The supernovae that created this remnant is a type 1AX. Now, Robert, I'm going to put you on the spot. Sorry, I apologize ahead of time.
Oh, that's fine.
What is a type 1AX? Have you ever heard of that designation?
I've heard of type 1A.
Okay, so that's the common type, is type 1A or type 2.
Right.
Type 2 come from the core collapse of massive stars, like what produced the Crab Nebula, for example.
Like Betelgeuse will do.
Like Betelgeuse will do whenever it collapses and goes supernova. Yeah. The other type, you want to explain the type 1A?
Okay, type 1A involves a white dwarf or a neutron star. They have certain limits to the mass. For the white dwarf, it's called the Chandrasekhar limit. And if you exceed that mass, the whole thing disintegrates. It blows itself apart. And that has a particular spectral signature to it that we can pick up and classify it. And I think its carbon lines are prominent.
Yeah, so you don't see the hydrogen
right.
and the helium like you would in a core. So it's from a white dwarf.
Right.
So the way you think of it as a massive star, the outer envelope of the massive star has a lot of, there's a lot of hydrogen throughout the star, including in the outer envelope. So when the core itself is made up of iron, when you get to that point, it can no longer support the weight of the star, so the whole star collapses starting in the inner region first.
Right.
And everything collapses down and towards the center, and then the thing blows, it rebounds. The core essentially reaches nuclear type densities. It can't collapse any further. So it's like all of a sudden it becomes extremely stiff, and that means material that's raining in from the outside slams into this really solid core and rebounds outwards. And it's in that rebound effect that generates the shock waves that blow up the star essentially.
Right.
And that material is hurled outwards. Now, from a distance, when we look at it, we see lots of hydrogen in the spectrum because it has lots of hydrogen in the outer atmosphere of the star.
Because that outer envelope is hydrogen and helium. And so it
Predominantly,
absorbs
yes.
that shock wave energy and re-emits it in certain wavelengths that say, hey, hydrogen's here.
Yes. Now, for this type that comes from a white dwarf, the white dwarf doesn't have that amount of hydrogen and helium.
It doesn't have
So,
that
in fact,
envelope.
white dwarfs are made up essentially of carbon. And so, if you see lots of that's your carbon lines, right?
Right.
You're going to when the white dwarf itself reaches that Chandrasekhar limit, about 1.4 solar masses, the white dwarf, which is made of degenerate matter, it cannot support the weight of that star. The whole star blows up. And how they blow up is mass gets transferred to the white dwarf from a nearby companion star.
Right.
And this really illustrates the stellar evolution. Stars are not, like static objects that never change ever for the whole lifetime of the universe itself. Stars do undergo significant changes, but it's over very, very long time scales compared to, the average human lifetime, right?
Right.
80 years or whatever. We're talking time scales of millions of years, some cases billions of years.
Right.
So when low mass stars end their lives, they become these white dwarfs. Our sun will turn into a white dwarf, for example. And so what will happen then is that if a star happens to be in orbit near another star, and that other star, which evolves slower than what turned into a white dwarf because it has less mass,
Right.
eventually you can have a situation where you have a white dwarf in orbit around a more normal star, and that normal star finally starts making significant changes because it's run out of hydrogen fuel in its core. So it leaves what we call in astronomy the main sequence of, and then that star will expand outwards. And if it expands and it becomes a red giant, then matter that's in the outside of the envelope of the red giant can actually be attracted more towards the nearby white dwarf than to itself in terms of gravity.
Right.
So some of the material then will spill on top of the white dwarf, increasing its mass.
And if it's slow enough, it produces a nova effect, right? It'll just ignite that material on the surface.
And what nova are we waiting for again?
That's
Corona
T
Brew.
Corona. Yeah.
Yeah. Still waiting for that one.
Yeah.
But if you have if the white dwarf has a mass that is near that 1.4 solar mass limit, then you can add some matter on top of the white dwarf to increase its mass. And you don't have to do a lot, maybe
Right.
0.1 solar masses of material or whatever. As long
And
as
it
you're
kicks it over. And
yeah, once it goes over that limit, it can't support that. The whole thing collapses, and the whole thing blows apart. Nothing left behind. The whole thing is driven outwards.
Right.
And you have, therefore, another supernova remnant of the leftover debris, in this case of the exploding white dwarf.
Okay.
Now, that's a 1A.
That's a 1A. So what does the X designator mean?
This is an unusual objects that were found fairly recently, last couple decades, been recognized.
Okay.
And remember, the more that you study any class of objects, the chances are greater that you're going to pick up some oddballs,
Right.
things that happen rarely.
The more people you study, the more people you're going to find are really odd. Right.
Well, the ones that you find the extreme examples.
Right.
Right, 'cause they
okay, 7 feet tall and higher.
Yeah, exactly.
The more you see, the more
NBA,
those you're going to find.
normal NBA type
Right.
of heights, right?
But how normal are they compared to the general population?
Yes.
Not very.
Right. So if you're looking at something that's one out of a couple thousand, and chances are it shows up, then
Right.
you need to look at a couple thousand before you have a chance of picking up one of these oddballs. It's that kind of law of
Okay.
statistics, law of numbers.
There you go.
Right. Now, what's weird about the 1AX is that when these stars blow up as type 1A supernova, number one, they're not as luminous. They don't produce as much light as
Okay.
the standard 1A star. And the other thing that's really bizarre, there's something left behind.
Oh, that is bizarre.
It is. In fact, this is an example of that case. The zombie star, the star that, if you like, lived through its death. That's where the term is coming from. So in the middle of this image that you see here, and the nice, sort of radial spokes that are pointing outwards, are the filament-like structure of the supernova remnant. In the very center, there's sort of a bright spot.
Right.
And that object, as far as we know, has the properties and characteristics that it's collapsing down to form a white dwarf. So it has survived the supernova explosion.
So enough material stayed close to the center that it's recollapsing into a white dwarf.
Yeah. Is that amazing?
That is crazy. That is wild.
Crazy. And that's why these things are subluminous compared to normal type 1A, is because the whole thing doesn't blow apart.
Right.
Partial explosion, partial detonation. What it really tells me is that we don't have things worked out in detail. In fact, I always wondered how you could get a white dwarf that's near the Chandrasekhar limit, so it's nearly 1.4 solar masses, and you dump material on it and get that material then to flare up. Think of a nova, for example, right?
Right.
So nova is far away from that, is away from that limit, right? Mm-hmm. So if you dump material, even if it's fresh hydrogen fuel on its surface, what's the temperature of the surface? 10,000 Kelvin, 20,000 Kelvin?
Right.
Let's be generous. 30,000 Kelvin?
Right.
You dump hydrogen. What's the temperature that you need to fuse hydrogen into helium?
A few million.
At minimum 10 million.
Yeah.
So how do you get hydrogen to fuse? That's dumped on.
Then again, you've got degenerate matter that it's being dumped on, so it's moving. It's got particles in there that are moving close to the speed of light.
Bingo.
That's what degenerate means.
Bingo.
So you've got particles moving quickly. They can overcome the Coulomb, the electric repulsion of the protons, and you get fusion.
Right. So it's not simply, analogy we like to use is you dump fuel on a bonfire and it flares up and then flares down back to the original brightness as a way of explaining the nova. But that's not exactly what's going on here because of the weird state of matter that the white dwarfs are.
That degenerate state of matter that's really weird.
Yeah, we have to be very careful on how all this stuff plays out.
Yep.
So, there's if you think about now these type 1AX supernovas, so here's a cartoon that was put together, and it was just a couple of years, well, it's actually earlier this year when these new results came out. And you can see the time evolution of somebody's model that helped to explain this type of supernova, these type 1AXs. So you have possibly two white dwarfs that merge with each other, that create this envelope that push the mass over the limit. And then you have, supernova explosion along with it as winds and shocked regions and just, all these sort of simple yet detailed enough that you're trying to reproduce all of the observations when you look at the spectra and take images like the sulfur image that we saw.
Right.
Trying to understand all of that.
And I will point out that that's one of the reasons we do use certain filters to point out different things. We use several different filters for oxygen, and in particular what we call an O3 filter. We'll use sulfur, we'll use hydrogen, helium lines, and we'll build filters that home in on that one color, that one wavelength. And it's because they tell us information like this.
And the mystery is, of course, why in one case, type 1A supernova, the whole white dwarf blows up.
Right.
Yet in this case, somehow it survives, or a piece of survive, enough that it coalesces afterwards.
That's what's interesting me. How did the piece survive?
Yeah.
To be the nucleus around which material starts recoalescing.
It reminds me right away of the discovery of planets around pulsars.
Right.
How did they survive? Or did they coalesce from the debris somehow afterwards?
Right.
So the original planets, if there were any, were completely destroyed. And then somehow material coalesced afterwards to form planet-like objects that are in orbit around. It's really, really strange.
It is.
The zombie star.
The zombie star. All right. So let's see. Yeah.
So these are the recent observations that the first slide showed that paper are all about. These are data taken with an instrument on the Keck telescope. So the Keck telescope, you see an image there in the top right. There's two of them. They're 10 meters in diameter. So they're essentially the largest optical telescopes that we have access to in the United States. The largest, by the way, in the world is in the Canary Islands. It's mainly owned by Spain and also Mexico. That comes in at about 10.4. And there's also a half decent size telescope, the Hobby telescope down in Texas.
Okay.
Right, so that's a large.
I've
That's
not heard
on
of that one.
Yeah, that's on the. It's a different type of technology, the way they put it together.
Okay.
So that's roughly a 10-meter class telescope as well, depending on how you count things. So, anyways, yeah, I'm
love that,
sure. I'm
depending on how
sure
you
there
count
are
things.
some arguments that people will make about who's actually got the
biggest.
largest telescope. But the instrument that was used on the Keck is known as the Keck Cosmic Web Imager Spectrograph, and it was designed to take detailed spectroscopic measurements of the cosmic web itself. So remember, that's the filamentary-like structure, the large-scale structure of the universe. And it has a new sensitive red channel. So people were using the instrument, that's sort of the best that they had now, up-to-date technology. In the image you can see on the left, on the top there, looking at the filament-like structure. In fact, you can observe in detail the details of the filaments themselves and get information about the expansion velocities. And you're talking on orders of like 1,100 kilometers per second. The material is flying outwards from the center region of the supernova explosion. And that allows you then to work backwards to get an idea of how long ago in the past did everything come from a single point. Yeah. And that's consistent with the 1181.
Okay.
So it looks like it's 100% that this PAL 30 that was seen back in 2013 is the supernova remnant from the supernova that was seen in the year 1181.
Okay, cool.
So here's a detailed image of the object itself, the supernova remnant. So on the left-hand side is the WISE image.
Okay.
And then on the right, superimposed, is the filament-like measurements that were made with the Keck telescope.
Oh, okay. So
it's
that's
all
the difference.
lined up spatially, and then the circle in the middle would be, the remnant. And notice there's a void in the middle too.
Which you would expect.
Yeah.
Blue.
Well, you have the
Winds blew it away.
debris, but inside the debris remnant, there's a void.
Right. Because some of it fell back on, and some of it was blown
some of it
away.
might have fell back on and helped create the thing that's turning into a white dwarf. And plus, that object is producing radiation, so there's going to be radiation blowing out from that as well.
Right. So the void makes perfect sense, is what we're getting at.
Yeah, so it's quite interesting from that point of view. So we're doing detailed images of this. I don't know if anyone has taken a JWST image of this object yet.
Okay.
I didn't notice that. But
would it be a target?
I'm sure it will be. It should be.
Okay. Should be.
Yeah.
I don't know. That doesn't mean it always is.
Yeah, I don't know if this group used the Keck telescope, so I don't know if this group or a different group is actually targeting it with the JW, and we just haven't seen the data yet.
Okay.
So maybe we'll have to wait on that. But it'd be definitely an interesting object to go at.
And it's definitely within JWST's bailiwick.
So I think it was today we got an announcement from the JWST people that the total number of proposals this latest round, the people trying to use the telescope, was over 2,500 proposals, like 2,700, I think the number was, or somewhere in that ballpark. Let's round it off, 2,500 proposals.
Right.
2,500 different teams of people are trying to use.
Let's see. If they each got time, that'd be 365 days, divided by 3. Yeah, they would get minuscule amounts of time. Hope you've got a bright object you're looking at.
Well, what I'm thinking of is who are the review panels that have to assemble review all 2,500 proposals. It's a big job. I mean, I've been on review panels before for ground-based telescopes, for the NOAO. It used to be called NOAO. It's now NUAR. They changed the name a couple of years back. But essentially the telescopes at Kitt Peak and in Mauna Kea and down in Chile. And it's a lot of work, right? You have to read the proposals very carefully, and you end up having to rank the proposals. So for those who don't know, if you wanted to use a telescope somewhere in the world, you just don't call them up on the phone or send them an email, say, I'll be there, next week to use the telescope. You have to actually write a proposal, tell them what you want to do in terms of your science, how you want to achieve your science goals, and then it gets evaluated by your peers. Mm-hmm. So other scientists then will review the proposals to make sure they're legitimate, right, that they're correct. But then eventually they get ranked, and in some sense you're at the whims of the interests of the panel that's ranking your proposals. They might think your science that you're interested in is not what they're interested in, so you get a lower rank.
Or sometimes it's good science, great science. They really want to fund this, but guess what? There's others that they think are better.
Yeah, there's not enough time on the telescope.
Not enough time.
There's a finite amount of time.
Yeah.
And the James Webb is heavily oversubscribed. There's no way they have the amount of time in 1 year and it's annual release of proposals
Right.
that they have to dish out to people, unfortunately. So you need, several of these telescopes. And
That would be nice, wouldn't
we
it?
still would use them
We'd
constantly.
Still, yeah.
So there's a great need for telescopes, especially space-based.
Right.
Once you get above the Earth's atmosphere, it's a whole new game.
Right.
I know Elon Musk, for example, is famous for saying, well, don't worry about the light that comes off of my Starlink satellites because you really should have your telescopes in space. And
Right.
therefore you would have to worry about those satellites. But
Okay.
the problem is it's costly to put
I was
telescopes
about to say,
in
when's
space.
he going to build one?
Well, the James Webb was over $10 billion.
Yeah. Well, he can do that
So-
about 30 times. So.
Yes, but where's the average, like NASA's not going to build one every year
Right.
and get funded by the government. The taxpayers are not going to fund that. So if it was a lot cheaper, in fact, in some sense, SpaceX is making it a lot cheaper to get
They
into
are.
space.
Yes.
So one can envision in the future that we send up raw material and then there's a 3D printer in orbit around the Earth printing out parts that ultimately get fixed to make satellites and even space telescopes. Wouldn't that be something?
That would be something.
And it'd
I
be a
hadn't thought
lot
about-
cheaper doing it that way.
So do we call that one DS9?
I don't know.
I don't know.
I'm sure that'll happen.
Yeah.
Well, don't forget the Star Trek movies, right? It was Star Trek.
That's what I was
That wasn't
thinking of.
built
That's
on
what
the
I'm
ground.
referencing.
It was all
Yeah.
built in Earth orbit.
That's what I was referencing.
Yeah.
This is, a big space dock where you just bring things into it to repair and ship them back out. And
Yeah,
where you build things.
Yeah, you just 3D print it. Wouldn't that be cool?
Yeah. So, all right. So, what's this one about?
So this one is the same supernova remnant. This is an artist drawing of what it looks like. And here they use the numbers that came from the recent paper. So expansion speed on the order of 1,000 kilometers per second. Those prongs that you see sticking out are those sulfur filaments that
Okay.
we've seen in the prior image. The inner core region is a dusty inner shell. And the actual core in the central region, you see like the bluish light coming, or whitish light sort of thing in the blue sphere, then is the hot inflated star that ultimately is going to turn into a white dwarf, as far as we can tell.
That really is just crazy. Yeah.
Now, here's something crazier.
Okay.
Is it possible that there's a surviving companion star to this object? And is it possible that in the future that object will transfer over enough material to this newly formed white dwarf that it goes supernova type 1A?
Well, wouldn't we see any companion star that it had?
I don't know if the material has cleared out enough to see that yet.
Oh,
Maybe. I mean, we need to look down into the core of this thing.
well, that would seem to me to lend itself to some radio observation. Get ALMA on it or something.
Well, JWST would see down in there a lot better
Okay.
than the Y spacecraft because that, even though it works at infrared wavelengths, the Y spacecraft had a much smaller aperture mirror.
Right. Less smaller mirror.
Yeah, so you're going to get a much smaller diffraction limit with JWST.
Right.
So you can see much higher resolution. And if not this telescope, then future telescopes. And then you wait a while for the stuff to clear more.
Right.
I mean, that's kind of like the problem with, remember the supernova 1987A?
Right.
And we're still waiting for the central region to clear out enough to kind of see what was left.
Right.
Is there like a neutron star hiding in there or whatever, right? And
Right.
So,
Yeah, it's a lot of hurry up and wait
yeah.
for generations.
Well, you can advance the technology, so that might give you a leg up on it,
Right.
but we need to see.
But we've got to see.
But anyways, that's the zombie star.
Okay. And so now what are we looking at? Oh, Planet X.
Well, I want you to read the title of this.
Orbit of a possible planet X.
Now, X is what in Roman numerals for us?
That would be 10.
That would be 10. How many planets are in our solar system?
8.
So I wonder if this is a subtle poke by the authors that Pluto should be a planet.
I don't know, but I'm going to point out that in 1934, within 10 years of its discovery, by 1944, people were questioning whether Pluto was a planet or not. So this isn't a new debate. There were reasons to doubt it to begin with, but you've got some personalities that were involved that said, no, it's a planet, so people went along with it.
Now, there's been reports, the last several decades now, of possible Planet 9,
Right?
as a lot of research groups are stating.
Yep.
So Pluto was demoted. I don't know how long ago that was now, early 2000s.
Early 2000s.
Yeah.
And I won't really classify it as a demotion. It is still a planet. It's just a minor planet.
A dwarf planet,
A
I think
dwarf
is
planet.
the terminology.
Yeah.
But Disney hates that
Well,
because they
yeah,
felt like they were like,
that's because one of their characters was named after it.
yeah. Now, the search for Planet X. So those papers, a lot of them that I've noticed that came out the last couple decades were based on the orbits of comets.
Mm-hmm.
And the idea is that there is a sort of a crowding effect of the orbits of the long period comets,
Right.
that would go way out past the Kuiper belt, way out into the Oort cloud, essentially.
And
That-
the crowding effect comes into play because they should, over time, spread out and be evenly distributed across the sky. And instead, we're finding them in clumped up into very specific locations, kind of like the asteroids in the asteroid belt, main belt, with the Kirkwood gaps.
Yeah. So those are resonances, and
They're
those areas
resonances.
gets cleaned out of asteroids.
Right.
So at the orbit in those areas, those distances from the sun are not stable.
Right.
So over time, they migrate out of there.
That's why they're hypothesizing the existence of this relatively high mass planet is because there are gaps, there are resonance type gaps in where we see objects.
Yeah. So this study is based on trans-Neptunian objects.
Okay,
So
T and
objects,
O's.
which means there's objects beyond the orbit of Neptune.
Mm-hmm.
And think of Neptune as the furthest planet from the sun.
Right.
If you don't think of Pluto in that respect. And once again, it's a study that uses simulations, computer modeling, based on data, to show that there is a clumping of the orbital characteristics of these objects. And you can see that on the panel on the left. And so if you can look, these are objects that have a semi-major axis more than 170 AU, okay, and less than 170 AU. There are two color codings. Darker color further away. The lighter color that you see near the center, of course, those are closer ones. Now, to scale, this plot then is 600 AU by 600 AU.
Oh, wow.
Yeah.
That's
They
huge.
give you a sense of scale. Now, the bunching up that you can see, especially in the dark ellipses, you see that the closest point to the sun then are kind of on the one side, right? They're not randomly distributed everywhere.
yeah, I
There's
see
a
that.
couple that are sort of extend to the upper right, but most of them are in the bottom left.
Mm-hmm.
And that's statistically, according to this study, significant. In fact, you can interject a planet then in the outer solar system to explain, and this is the computer modeling and simulation part of things, what type of planet in terms of its mass and in terms of its orbit would give rise to this effect that you're seeing here.
Okay. I'll buy that for $1.
So for the numbers that they run, then here's what you get, and this is given on the right side. Mass of the planet, about 4.4 plus or minus 1.1 Earth mass.
That's a pretty big error bar.
The semi-major axis, so that's the
200
average distance of the planet to the sun, 290 plus or minus 30 AU.
Okay.
And an AU, by the way, an astronomical unit, is the average distance of the Earth from the sun.
Right.
So think of Pluto. Its semi-major axis is 40. We're
Right.
talking about 290.
So it's this thing's error bar is about the size of Pluto's orbit.
Yeah, it's like the size of the solar system
it's-
that we normally recognize.
Where I said the first one on the mass was pretty major, significant. The one on the semi-major axis is not.
Well, think of the Voyager spacecraft. They haven't
Yeah.
even come close to getting out to 290 AU.
Right. They're at what, 80?
It's like 100 and some for the furthest one, like
Okay.
160 AU or something like that.
Something like that? Okay.
Wouldn't it be serendipity if one happened to go out on a trajectory that came close to another
found
unknown
it.
planet and found it? Because then it went by a curved trajectory that we could easily measure and say,
Right.
okay, then you can pinpoint where it is and how much mass it got.
Right, because of its effect on the satellite. Yeah.
And too bad there wasn't enough thruster fuel on board. It could go into orbit and turn on the camera again
Right.
and get observations of that.
That would be serendipitous.
That would be more worthwhile than having the thing just go continually move out of the
Yep.
solar system and go in orbit around the center of the Milky Way.
But that would be such a horrendously lucky shot. that would be one of those shots of, wait, what?
Yeah, better odds of winning the Powerball and the
Yeah.
Mega Millions 10 times over
Right, I was about to
in your
say.
lifetime, right? Each one,
Winning the Powerball is more likely.
for sure. But it'd be quite interesting. Now, the shape of the orbit, when orbits are spherical in shape or round, as we call it. They have what we call eccentricity of 0. And if you stretch it out till it becomes a line, that's essentially an eccentricity of 1, and that boundary, the extent. And so this orbit is estimated to be about 0.29 plus or minus 0.13. Now, the Earth is just a little bit more than 0 because the Earth is not in a perfect circular orbit.
Right.
It's slightly elliptical, but very slightly. In fact, that's why we say in July we are the furthest from the sun, and in January we are the closest to the sun because we're not in a perfect circular orbit.
So 0.29, that's pretty eccentric.
You're talking about the type of orbits that you see here on the plot for those asteroids, right? The trans-Neptunian type objects. And the other thing is the inclination, which is interesting.
That's a pretty low inclination.
Yeah, 6.8 plus or minus 5, which means it's close to the plane of the solar system. In fact, that's where you'd expect all of the major planets to lie, and the only one except, Pluto, if you want to include Pluto in that list, all of the other ones, including the Earth, are really close to the plane.
7 degrees, I think.
Yeah, just a couple degrees for some. And so the inclination is relatively low. So this is a relatively low inclination, but it matches what you'd expect of an object that was made in a proto solar system nebula, right?
Right.
So it's interesting. And the plot that's on to the left of the text, but to the right of the plot, the panel that's on the far left, gives you some idea of statistics, like what is the probability of having certain values of, for example, the distance in AU, the latitude, the apparent magnitude. So the apparent magnitude, you're looking at brightnesses on the order of about, 21 magnitude, 21st magnitude.
Okay. So so for something like James Webb or similar, this should still be a fairly easy target to spot.
Well, the thing is, you're looking over a huge area. In fact, the authors of the paper, now, the authors of the paper are no slouches. The third author is a very famous person who is very smart and wrote the textbook on orbital mechanics.
Let's see, who is that name again?
Scott Tremaine.
Scott Tremaine, yep.
In fact, he's a Canadian.
Yep.
And he's in Princeton, at least the last he's still there, Institute of Advanced Study in Princeton. So he's a very smart person.
Oh, yeah.
So this paper is done right. It's not just, people doing this topic for the first time and they're usually, they don't really know all the ins and outs of the trade.
Right.
This guy knows it.
He knows what he's doing.
So, yeah, it's worth a read, this paper. And so what they suggest is that maybe in the future, the Vera Rubin Observatory that we just talked about that saw first light with a temporary camera is going to scan such a large part of the sky, like I said, the whole southern hemisphere, every 3 nights, it can pick up this type of object.
Right.
So one of the things people are going to be looking at, there's going to be lots of teams of astronomers, even amateur astronomers, that are going to try to process that data looking for a planet-like object in the outer solar system.
Yeah, and that's kind of what I've been waiting on. I mean, I think these modelers are great. I think what they're doing is great. I don't doubt that they're based on data, that they're based on what is known, but I want to see this planet before I'll say, yep, it's there.
Yeah, I mean, people have been looking, too, with smaller ground-based telescope, 4-meter class, and I think even 8-meter class telescope looking for these type of objects.
Right.
And they haven't seen any yet. And they're probably getting disheartened because it's been more than 10 years, as far as I know. They're probably getting closer to 15 or 20 years they've been searching it. And nothing. So
nothing.
Then you have to explain why there are these sort of coincidences in the orbital parameters of these objects.
Right. And that I don't have any good explanation for either. But I for a planet to be there, I want to see the planet. It should be bright enough, especially at the masses that they're talking about.
Yeah, it makes you wonder. I mean, people obviously looked at a nearby passing star in the distant past, what effect that has on the orbits, and also on how they actually formed to begin with. Is there any process that would cause a bunching up of these orbits in the very beginning of the formation of the solar system itself, when the debris was being cleared?
And the further away from the sun you get, the more that type of thing, artifact, that's a good word for it, lingers, because there's nothing in there to disturb it and break it up.
So what it really means...
we don't know.
Yeah, to summarize is there's a lot of information that we need to gather about the outer solar system.
Yes.
It's a real question mark.
So we need more probes. Call your Congress critters.
Yeah, a real question mark right now. Now, this is an interesting image. This is taken, or I should say released just yesterday by NASA.
Okay.
And is 9 potential landing sites for the Artemis 3 mission in the south pole of the moon.
Okay, so this is the moon, and that's the South Pole is the little green star in the lower center.
Yeah, and the yellow boxes represent potential landing sites that they picked out now. And
Okay.
of course, landing sites, you want to be able to go somewhere where it's safe to land, number one.
Right. So I would think that peak near Cabeus B over on the left is probably not the best site.
And you want to go somewhere where it's interesting geologically.
Okay, that might be why you would want to land there.
And then you want to go somewhere where you think there might be water, that'd be taken near the crater areas that are under
Right.
shadows that you see there. That maybe it's under permanent shadow, that maybe there's water there. And that's always been one of those things that probes have hinted at, and others have said, no, it's really not much there. And others, yes, there's stuff there. So we have this fuzzy understanding
Right.
of whether there is water there in an amount that could be useful.
And that's the trick. Is there enough to be useful for future landings and bases, potential bases?
So this is for Artemis 3, and you might say, well, wait a minute, we did Artemis 1. That was the unmanned launch of the SLS. It's been a couple of years now, hasn't it?
I think it's
well
a year
over
or
a
two
year
now,
ago.
yeah.
And the Artemis 2 is the one where you're going to send NASA astronauts and a Canadian astronaut around the moon, orbit the moon, and come back.
Okay.
Okay. And then the third one is when you're actually going to attempt a landing. Now, this is the interesting part of it all. Number one is we don't have a landing craft right now. And we want to do this. First, it was, I won't go through all the laundry list of dates, but the last we hear is like 2026. But you know how close 2026 is?
2 years.
Well, in a
Less than
couple
that.
months is 2025.
Yeah, so a little over a year.
So are we going to be able to do this in 2026? Now it's 2027 maybe. They keep pushing it back. Maybe it's going to be in 2030 when it actually happens. You know, these kind of time frames always slip, unfortunately.
Right.
And the reason why they slip is for various reasons, including not having enough money or financial support, and not being allowed to develop your spacecraft in the right type of time scale. And the reason I say that is both SpaceX and the Blue Origin have contracts to build landers. In fact, SpaceX, as we know, the Starship is supposed to be the one that
Right.
does that. And I think SpaceX has been arguing for a while now that they have to go through so much red tape. The FAA and investigation and all this, and EPA was looking at their site in Texas and all this, and they can't do what they want to do on a short enough time scale to guarantee that they can meet the delivery of a vehicle by, let's say, 2026, which was our first hope. In fact, of course, it was 2024 before that and 2022, but now it's 2026. And because of all this, I mean, we've just recently seen, the 5th flight of Starship?
Right.
And there could be, maybe we need 50 of them to perfect the technology to the point you're going to risk to put astronauts on board the Starship and having it land on the surface of the moon and then be able to take off again.
Right.
And you don't want to just crash land because then that's it.
Or despite what Elon was saying about landing on Mars, we really don't want to send people just to leave them there to die.
Yeah, especially we've already sent people to the moon.
Yeah.
And brought them back.
And brought them back.
We don't need
we did
to-
it, 7 times?
6 times, I
6
think.
times. Okay.
Yeah. So
Should have been 7, but one of them
Apollo 13.
ran
So
into
there was Apollo
problems.
11, 12, 14, 15, 16, 17.
So 6 times.
So 6 times. So that'd be 12 men have walked on the surface of the moon.
Yep. And
altogether.
it's so sad that we've delayed things long enough that we've got to relearn how to do all of that.
Well, that's it. I mean, the landers, I don't think, in my personal opinion, are not getting enough support.
Right.
And NASA, of course, is like, well, they're up against it because they have their federal government agencies, so they don't want to do too much to the federal government and complain, probably. 'Cause They're
Right.
scared of funding. But they don't want it to go so that the government delays things so that it's not ready for 20 more years, because that's not good either. So it's a sort of a happy, it's a fine balance that you got to,
There
fine
is.
line you have to walk.
Yeah. I mean, there are reasons, but at the same time, it's sad. You know.
And Blue Origin, you don't even see what's going on with them. They keep
No.
everything pretty close to the chest. They hide things, and it's not very public.
And in fact, the last thing I ever heard is they were trying to use perfect being able to use methane as fuel.
Yeah, well, that's what SpaceX is using.
Oh,
right?
they are? Okay.
Yeah, they talked about using that.
Because there are definitely problems with using it for consistent flow and things like that.
Yeah, so when a lander actually gets built, that will determine the time frame in which Artemis 3 will actually occur.
Okay.
So it's a wait and see. So maybe the early 2030s before things are perfected, where you're ready to take a chance.
Right.
The technology has been proven. Who knows? Wait and see on that one.
Yep. So.
There should have been one more there.
Nope.
Oh, that was it.
That was it.
Yeah. Okay. Guess because I had some items here I wanted to talk about, but I didn't make the slides.
Didn't
for
make
them.
the slides for them.
Yeah.
Okay. Because you.
Yeah. So we talked about Starship 5. Did you see the last one?
I did not. I'm not a big spaceship guy.
Come
I
on,
love
Robert.
what they do.
You're
but
not
I
a space cadet?
I don't. I've never been one to really get into watching rockets go up. Sorry.
Anyways, the last one was caught by the chopsticks.
Right. I did know that.
You did know that. In fact, there's a report that came out a few days ago that the engineers were talking openly to Elon Musk about what actually happened. And, when things, you go back and you look at it in detail, right?
Right.
How things occurred. And it turns out that the spacecraft was 1 second away from aborting.
Oh.
And abort mode would mean you just fly off and land somewhere away from the landing area,
the
right?
gantry.
The gantry and stuff. So that almost happened, 1 second away.
Wow.
Because I don't, maybe the engineers didn't think that this was actually going to occur the first shot. Probably not, because there's so many things that had to go right.
Right.
Right?
I mean, yeah, there's so much that can go wrong.
So now they can go back and look at that and ease up on their limits and then don't make it so harsh in terms of abort modes and things like backup plans.
Well, that's something a lot of lay people don't understand. You want things to go wrong on tests. You want them to go wrong, because where you don't want them to go wrong is when you're not doing tests. When you're doing the real thing, that's where you don't want things going wrong. So you want it to all happen while you're testing it.
And don't dare mention the name Boeing when you think about that.
Boing, boing, boing.
Boeing
Boing,
has,
boing, boing, boom.
Yeah, Boeing has crawled down that avenue, you see,
Yeah.
unfortunately.
I feel bad for them, to be honest.
The latest I heard, I don't know if it's true or not, I didn't look into details, but they're talking about selling all of their space industry, their space side of their business.
Wow.
The Starliner and everything is up for sale potentially.
That's kind of crazy.
Because they ran into a lot of problems. In fact, they couldn't bring the astronauts back from the International Space Station a month or so ago, whenever that was. And they lost a lot of billions of dollars. They lost a lot of money. And then in their aircraft and all the problems they had. So, yeah, not good. Now, the other news item I wanted to mention briefly is that, and we talked about the James Webb Space Telescope, it actually made observation recently of Vega.
Oh.
Now, why would you want to look at Vega, which is an A0 type star?
I can think of a lot of reasons you want to.
Why would you want to look at it with an infrared space telescope?
Probably to see if there's planets around it.
And why would you think there'd be planets around?
Well, I would not think planets were around, because that high massive star has too high a solar winds. It should have blown off its envelope, its protoplanetary disk, too quickly. And number two, because it evolved so quickly due to its high mass that there wouldn't be time for planets to form.
Do you remember the movie Contact?
Yes.
Do you remember that in that movie Contact, the signal came from Vega?
Okay.
And there was a point in the movie where Jodie Foster was arguing with the quote-unquote director of the NSF or whatever it was.
Right.
And he had mentioned something why it would not be Vega. Do you remember that? In fact,
I don't remember that.
You don't remember that part? And in fact, when the signal first came in, that was detected at the VLA, I believe it was.
I think so.
The two guys that were at the computer terminals at the time
Discounted it.
started discounting it, and they had a reason why they discounted. Do you remember the reasoning?
If I had to guess, and that is just a guess,
Okay.
is Vega is too radio noisy to begin with.
No, actually, it has a debris disk. That was actually true. We found that many years ago.
Okay.
So there is a debris disk around Vega. And Vega's about 25 or so light years away from us. So what the James Webb Space Telescope observations are looking for is planets around Vega buried inside this
The debris disk.
debris disk. So there is material left over. But
Okay.
did planets form, early on?
Right.
It's all connected to this type of material.
Like I said, there would have been strong winds to blow it away. There would have been all these problems with them forming. So, did they form?
And
Good
the
question.
answer is no planets were found around Vega. It does not have planets, at least to the limit of what they
it
can see.
resolve.
Now, the limit I noticed was somewhere between 2 and 3 Jupiter masses.
Okay.
So what's the Earth like? Jupiter's like 390 times the mass of the Earth of that order. So you're talking 2 to 3 Jupiter masses. And some people have made the argument that no, actually, because if you have a planet at least 0.3 times the mass of Jupiter, that's enough mass to disrupt the debris disk. And because we don't see the disruption, right, that planets have to have a mass less than that value. So let's go with the lower limit, 0.3 Jupiter masses. That's still about 95 times the Earth mass.
Okay. So they could still have planets, but they're definitely now in the realm of they're smaller.
Yeah, they have to be smaller planets just because you would see the disruption that they would make in their orbits, the gravitational effect, right, of the debris disk, and we just don't see that. So that's quite interesting.
That is interesting.
Yeah.
I didn't know about the debris disk. I knew about other things.
And that
like
was, remember, because
high
there's one line in the
rotation
movie
rate
where the
and
guy,
things like that.
well, it has a debris disk. How could people survive? Oh, you blast them with your photon torpedoes. You remember the line in the movie?
It's been so long since I've seen the movie.
If you rewatch the movie, you'll hear that part. And that's what they're referring to as that debris disk.
Okay.
That it's a young star, right?
Yes.
So how do you get intelligent life that be able to contact other civilizations on a planet orbiting a very young star? And the other thing is that debris disk, that any spaceship in around there would get hit, bombarded, and so maybe life wouldn't even form on the planet to reach the point where you can send off radio signals.
Who says it had to originate?
Well, that was the thing. It didn't originate there. That was the wormhole, and it actually came from another galaxy, suppose.
Right.
That's the gist behind the storyline of the movie.
It's a good movie. I haven't watched it in a while, but it's a good movie, folks. If you wanted one that's
so that's Contact.
Yeah,
and
Contact.
Carl Sagan wrote the book that the movie is based on.
Yep.
So there's a good plug there for it. Anyways, talking about plugs, one of the things we'd like you to do, of course, is to come to the University of North Dakota and investigate the different programs that we have, both on campus and online. If you are interested not only in STEM, but anything, just to get educated, the different things that you might find interesting, or if you're not sure what you're interested in, then look at all kinds of things. You never know. You stumble across something that you didn't really realize that you're interested in learning more about.
Heck, I'm enrolled in one of their certificate programs. So
there
come
you go.
join us.
Now, our next podcast, next Tuesday, is November 5th. And we always leave a quote at the end of our podcast.
Right.
And since we've talked about supernovae and stellar evolution, the quote is actually from Hans Bethe,
Okay.
who won the Nobel Prize for his work that was published in the 1930s that uncovered the details of nuclear fusion, the conversion of hydrogen to helium in the core of stars like our sun, for example. And he also did a lot of work near the end of his life. He lived, I think, into his 90s, so he lived a really long life.
Nice long life.
Yeah, and a lot of the work he did at the later stages of his life was all based on supernovae type of work.
Okay.
So it's actually fitting.
So it's fitting.
And it made sense because he actually did a lot of work on the Manhattan Project. He's one of the key players. So he talked about, he's working on nuclear bombs.
Right.
So let's go to nature's most powerful bomb, that being supernovae.
Supernova.
So here's the quote. Stars have a life cycle, much like animals. They get born, they grow, they go through a definite internal development, and finally, they die to give back the material to which they are made so that new stars may live.
Woot. All right.
Thank you very much for watching.
Thanks,
Please
folks.
give us a thumbs up and subscribe if you haven't already.
All right. Y'all have a great week. We'll see you next time.